Good morning, everyone. So my name is Jesse Villarreal. I'm from Texas Instruments, and I'll be presenting to you today the safety critical extension to OpenVX, which was also released this last Monday. Okay, so a lot of, OpenVX is targeted at embedded applications, as we've said, and many of these applications are going to be in safety critical systems. At least that's one of our stated goals of the OpenVX spec. And so really we started a little bit over a year ago a safety critical subgroup of the OpenVX standard that would just meet in addition to the regular meetings, so we could do things in parallel much quicker, working toward facilitating implementation of OpenVX into safety critical applications. So that was the whole focus of the group, and this is what has produced this extension that came this week. So when I say that the OpenVX safety critical extension is targeted to safety critical applications, of course we cannot guarantee that any implementation that somebody goes and makes from the specification is itself safety critical. But the whole idea is that we could facilitate those implementers from the start, looking at the spec. So software written for safety critical applications, they require rigorous demands on the deployment software and the development processes. So if you look at ISO 26262, this is one of the industry standards that has all sorts of requirements about how do you develop your software. There's all sorts of processes regarding how do you test this and tracking of requirements through the whole process and testing of those requirements and so on and so forth. And a lot of times what you'll see in the industry is something similar to this. This is just a V model for safety critical development process. And so all these arrows are talking about it's the connectivity of, you start off with your requirements and all the requirements of the requirements that you have to make, going through, filtering to the architectural design, the implementation, and then coming up on the right-hand side, this backtracking and backward mapping of, okay, now I go and test the implementation, I test the integration of all these subcomponents, and then finally the system verification. So every requirement has to have at least one test. And all of this has to be connected in terms of the development process. So I'm not going to go into more detail on this, but I put this up here just to point out where, as a spec writer, can we influence, can we facilitate this process. So we've highlighted a few areas. Obviously, requirements is a big one with regard to OpenVX. In the spec, we can highlight those requirements, and we can make sure the requirements are clear and pointed out. So that was. We'll talk about one of the areas that we focused on. Secondly, with the implementation, since OpenVX does provide header files, at least that portion of the small portion of the implementation we wanted to make sure is conformant, and we'll talk about that. And then the entire right-hand side talking about verification, we'll talk about that too. So that's kind of where we focused in on, so I'll go one by one. So in the area of requirements, one thing that we wanted to do was go through the entire spec and at least annotate where each of the requirements were listed in the spec. So we started from the existing spec of 1.1, and we looked at, okay, if this is a requirement, we wanted to spike it out so that can be used to generate documentation and can be easily referred to as we move the spec from one generation to the other. These requirement numbers will stay the same. Of course, we'll add new requirement numbers if necessary, or remove requirement numbers as those requirements might be de-scoped. And so this is kind of the example of what we've done. Each requirement is identified with a tag. So it's these open and closed brackets with an R and a 5-digit number in there. So as you go through the spec, the safety critical spec, you'll notice, first of all, these tags everywhere. Okay, so second, as I said with the implementation, there's a standard called MISRA C. And so for those of you who are not familiar, this basically is a put some additional rules on top of C. For anybody who writes in C, you could really shoot yourself in the foot if you don't know either if you don't know what you're doing or if you're just not very careful in what you're doing. So what the goal of MISRA C is to put some extra rules, and I'll give you some examples. There's a lot of rules that focus on portability from one compiler to another. And so, where some compilers may vary from others, they wanted to make sure that they'll put some rules into place that all known compilers will support at least this. And so let's make the code do that. So Another example that I see a lot of when I was looking at code to try to do MISRA C compliance is the use of explicit casting. So a lot of programmers may take, for example, an int plus an int and an int plus a short and assign that to an int. Well, there's a rule for that. They said, no, if you're going to do that, you have to cast everything to the least common denominator. So you cast your short to an int or vice versa, something like that. And there's a whole host of lists of rules, and I won't go into it here. But from the point of view of the header files, we wanted to run this through. There's some static code analyzers, and there's some rules checkers from Mr. C. So we went through that, and some of the changes that we had to do was where we had some enumerations already there, changing those to pound defines, and I won't go into why that's a rule. You can look at the Mr. C standard for that. The Mr. C standard also has some issues with unions, and so there was a couple unions that we had to add some variant tag so that you don't shoot yourself there too, depending on compiler portability. So other than the Mr. C, there's some other aspects of the APIs where, for example, the initial specification would say something like, just for informative purposes, it would say the undetermined behavior. If you do this, that's undetermined behavior. Well, if you're doing a safety critical application, you don't want undetermined behavior, so we would have to make those types of changes to define what the behavior is in these cases. Other cases where there's pointers to objects, and there's no defined size. And so for safety, you want to be able to check the sizes of the pointers before you access the data within those buffers. So those types of changes we've gone through and changed. And I'm sure it's a big spec. There may be others that we've missed, and so that's where community feedback can be useful. So I encourage you, if you're in the safety critical domain and you want to take a look at this, we're going to be making revisions to this as we go forward. So another aspect, and I think this is where you'll see the most changes beyond perhaps the tagging we have for the requirements, is in the verification. So if you're in a safety critical domain, you know that verification testing is a very expensive process. If you're going to be deploying software, that has to be rigorously tested. And so one of the tools, one of the approaches that people would like to do is to move, the tests, the code generation from perhaps what gets deployed to what is just a tool. And what I mean by that, and we've already talked a little bit about this deployment feature set versus a development feature set, is if you are, there's a lot of code in OpenVX that is related to creating graphs, creating data structures, creating nodes. And if you're going to be deploying that, I think as Radha had said, you don't necessarily need to be doing that every time you turn on the car. There's no need. If you don't need that, then why do you want to test that? So we can reduce the amount of testing that is done by reducing the amount of software that actually gets deployed. And so kind of shifting a lot of this software over just into the development domain and minimizing the amount that stays in the deployment domain is kind of the goal here. And the idea here is that the tools that you use to generate the software or to generate what gets deployed doesn't have the same stringency of, it still needs to be functionally correct, but it doesn't have, if you're just operating a simulation on a PC, you don't have real-time requirements necessarily for that code. You don't necessarily need the fault tolerance, the error condition recovery, the deterministic behavior. You could do potentially mallocs on the PC because if it crashes, you're not killing anybody type thing, versus you can't do that sort of thing in a deployed system. So again, just kind of the idea of moving a lot of this over to a development platform and minimizing what goes into the deployment platform. So I'll talk the next couple slides. So these, if you look at the spec, chapter 2.19 talks about this concept of deployment versus development, and 2.18 talks about the import-export framework. So I just wanted to note that the import-export extension is a standalone extension, but the safety-critical extension also requires that, so that as that extension gets incorporated into the safety-critical extension itself. Okay, and you've seen this slide, I think, from Radha before, and I just kind of talked a little bit about it. So if you imagine yourself on a PC of some sort doing the development of your graphs and creating the graphs and all the objects, doing your testing there, and basically you've got it to, like you want it, then you can export this into some vendor-specific binary. It doesn't have to be, it could be header files, it could be whatever the vendor has defined from these tools, so that can somehow get imported into the the deployment environment at runtime. And I just wanted to note also that at least for that particular vendor, since it is a vendor-specific format, you can go back and forth between this format and refine it, do some additional validation, do some additional optimization. So this is going to be something that's not the spec defines, but because the vendors can have these types of extensions as well. Okay, so again, I mean, when we try to define what goes into the deployment feature set, we kind of kept in mind, let's minimize things. And so we don't need, so what is needed in the deployment, for example, obviously is the import functionality from this object, creating and accessing the graph input and output data objects, right? You already have buffers that the camera is giving, and so you need a means by which to connect that to the graph. And so we thought in mind of having those types of functions. And then, of course, the functions required for processing the graphs. And then there's a whole lot of things that really can be stripped out that are not needed in deployment. For example, the VXU immediate kernels, we haven't talked about that in here yet, but you can look at the spec. Those are kernels that happen outside of the context of a graph. And so we felt, let's focus on the graphs here. So graph construction, graph verification, and again, a lot of the overhead of graph verification, there can be some optimizations there. There can be some checking. If that's all verified offline, you don't need to do that again during the deployment. Logging and performance features, and of course the graph export. It only goes one way in the deployment. You can just import. Okay, so when you look at the spec, we identify what functionality is in the deployment feature set by a table that's much larger than this. This is just a sample of that table, so it spans a couple of pages. So you can easily see which functions are in the deployment feature set. Okay, so this is a summary of what I've talked about. I want to give a couple minutes for questions, but just a couple points here is looking forward. This is something that we're talking about in the group. We haven't decided yet, but now that we have this first release of the spec out, there's some talk about seeing if we can merge everything that we've done here into the next version of the spec, or if not everything, then maybe a good portion of it. So hopefully we'll see what happens with that. And again, I just want to call out, if anybody is in the industry here, we could always use some additional help, some additional insight, some feedback for the use cases and how we move forward the safety critical aspect of OpenVX. Does anybody have any questions? Yes?
So I have one question. So I'm sorry if I didn't pay attention all the way, but I think what you described were mainly kind of like requirements for the development of the OpenVX.
Yes.
API,
right?
Are there any requirements in terms of the user of OpenVX API?
So I think one of the guidelines we had, and Radha, you can correct me if I'm wrong, is we were focused on the implementation aspects of the OpenVX, and so we did include in this list the requirements on the user. Is that right, Radha?
Yeah, I think the safety critical is mainly, like Jesse is saying, it's mainly designed from an implementation perspective, because when people take this specification, they're not going to just use OpenVX as a separate company. They're going to just put their whole app together. That's the feedback that we got working with.
So implementer and so essentially the suggestions are put into the API itself, into the implementer.
Yeah, basically, if you try to look at a safety critical application, I haven't personally worked on that, so I don't know much. Based on what I heard, the feedback that I got from is safety critical is more for an application.
Yeah.
What we're trying to do is we're trying to define some kind of a guidelines on top to make an OpenVX implementation more easier for somebody to take it and make it into a safety critical application.
And one thing I didn't say, but I just want to make sure it's understood. If I want to take OpenVX into a safety critical environment, I don't have to do this deployment feature set. It's not the only way. You could have the entire of OpenVX put into a safety critical system, but you have to consider the additional testing required for all those additional APIs. So this is something that we're doing to make it easier as an option for people, how we think they might want to do it. But there's very well could be implementations that have more than just what's in this deployment feature set, if not maybe the entire OpenVX. Yes?
So from a question I asked earlier, it sounds like the graphs can be created and verified and then stored into some kind of binary and later loaded. Does the OpenVX and the safety critical have a means to, again, when you load that binary, re-verify at that point?
I think right now the semantics are defined that we assume that it's already verified and we don't need to go back and re-verify it. So if there's a use case for that, then we'd be interested to hear about it, though. Yes, sir.
So this means that practically the application is just as safety critical as the implementation of the open
Absolutely.
itself. So this scheduler is the weak point, maybe, I think.
It just depends. Really, it's up to the implementation. But I mean, if you're anybody who's putting any software into a safety critical system, you know, they're just not going to take something off the shelf unless it's been certified. I mean, they're going to be responsible. So there's going to be potentially, if a vendor is making this system that's claimed to be safety critical, whoever's putting it in that final system is going to want to see that process and how it's done, and you know, you can imagine.
How do current implementations in this aspect? So are they safety critical? Are there any certifications for this, or it's not yet?
I don't know how to answer that. You'd have to ask the different vendors. But yeah.
So one thought would be to use some kind of checksum. So if you had a bunch of binary, if you had created a bunch of graphs, and if somehow one of them got scrambled, but they were being loaded at runtime on the fly, and you were worried that something had happened and that could cause a catastrophe, maybe you could embed in the graph, in the binary, some reference point, not a blockchain.
Sure.
You don't go all the way to like, hey, what's the history of this?
Yeah, and from the specs point of view, we haven't talked about that at all. That's, as you can tell here, when we have this box of, you know, vendor specific, that shortened the scope of what the spec is going to be talking about and kind of pushed the burden out to the vendors. Oh, that's a very real, security is an issue. Right, I mean, in this binary may not necessarily reside something, this could be within the closed system once you go to production, right? So, yes.
I was actually curious, is there any means that the test or specific feedback, if there would be an error of saying, like, if you had precompiled something and you ran that binary, but you had since then updated the runtime, like that's, if there was a runtime update and would cause things not to work as expected, does it actually give you that much information, or does it just say error?
I mean, the spec doesn't define anything regarding that. That would have to, again, be an implementation-specific way of checking versioning or something like that. That's good feedback. That's going to be my answer for almost everything, right?
Great ideas. What we don't want to do is add things that are really specific to some kind of hardware. Okay,
right.
But these are not, right?
Right.
These are things that we could put in the spec and say, look, if you're going to, you see. So I'm marking these things.
This is good feedback. I agree. Okay. Well, thanks very much.
So I am Thierry Leplay, and I work at Cadence. And this session is going to be, well, to focus on the OpenVX import-export extension. So here is the agenda. Yeah, I need to wait a little bit after each slide. So I'll start by presenting the import-export functionality. So I'll take 10 minutes for this. So I speak about the principle and more important, the API. And then we'll move to the hands-on, where we should have two exercises, one for export and one for import. So you need to work a little bit there. So there is some code with some holes that I'd like you to fill. And for this hands-on, we will use as a use case a Keypoint detector and tracker. So the same kind of application that Rada was discussing about at the very beginning. But of course, this import-export principle will work also on the neural network graph, like what Tomer was presenting. So now let's get started with the import-export principles. So we already talked about this today, so I'm going to repeat again, but I think it's important. So in this slide, this is a standard way of using OpenVX. So you create data object and graph, And then once all this is done, usually you are going ahead of time to verify the graphs, and by calling VX verify graph for each graph. So this is where validation and graph optimization already happens, so it can be time consuming. And from this point, this is where you are going to do the actual computer vision processing. So you are going to execute these graphs, taking data from the camera. So this way of working is fine on high-end systems like the desktop systems or high-end mobile systems. But when it comes to embedded systems, to real-time embedded system or like safety-critical systems, we usually prefer to push all the overhead, and typically the graph validation and optimization overhead, we prefer to push it offline. So this is where the import-export extension comes into the picture. So the application, or the developer, is still going to create data objects and graphs as usual, using the OpenVX API. But instead of verifying the graph and using it directly, he's going to export data objects and graphs that he finds useful. And this export process is going to generate a binary blob that is vendor specific. And so this work can be done totally offline on the development system, so typically desktop. And graph validation and optimization, should happen at export time. So there is nothing in the spec that enforces this, but all implementers are going to do this, because the purpose of export-import is really to move all the overhead offline. So we want to have this graph optimization and graph validation at that time. Then, on the deployment system, you can re-import this binary blob, and the OpenVX runtime is going to create, to recreate some objects, some OpenVX objects, the ones that you exported, and then the computer vision processing can happen. So the import is typically going to be done ahead of time again, but compared to what we had before, it should be light, because obviously you are not going to optimize and to validate graphs at that time. You are just going to load this blob and potentially do some initialization, but and maybe some memory allocation, but it should be relatively light. So what can be exported? So any data object can be exported. So you can pass to the export function anything like a VX image, an array, a pyramid, a scalar, anything. You have the option to export the value of this object itself or not. So typically, for instance, when you are going to export an image, so usually you just need to export the dimension of this image. You don't need the data because the data are going to come from the camera on the deployment system. But if you want to create a demo, or maybe in some particular cases you want to have a constant data, like you have at import time an object to be pre-initialized, so you can tell, okay, at export time you can put the data you want into this object, and when you specify that you want to export this object, you tell, okay, I want to export the value too. And for instance, for the image, the value will be the pixels. You can also, we were discussing about delay objects, so we can export also a delay object that is a sort of container that contains multiple data objects. So I make use of a delay object in the hands-on session, in the hands-on code. What, of course, and it was a question we had, I heard before, so yeah, we can export graphs, and this is, I believe, the main purpose of the import-export extension, because the graph is where all the computation complexity, where all the computer vision processing is described. and we want to be able to export, to create potentially a complex graph on the development system, then we optimize it and we export it as a binary blob, and then we re-import it on the deployment system and just run it. Something important also is that the relationship between the objects that you export are going to be preserved between export and import. So for instance, there are plenty of concepts that we didn't speak about the region of interest in the previous presentation, but this is an important concept from OpenVX, because you can define an image as a sub-region of interest of another image. So when you modify one of the image, it is going to be automatically reflected in the other image. So if never you export an image and a region of interest of this image, so you have two separate objects, but that points to the same memory. So when you export these two objects, at the time you are going to import it, you are going to get two images, and the second one will still be the region of interest of the first one. And this is the same also for data objects and graphs, because typically a graph is going to get is going to be connected to some input images, for instance. So when you export the graph and the input image, you are going to get at import time a graph and an image that is already connected as the input of this graph. So this is a very important concept. And to finalize with this overview of the import-export, with this import-export presentation, I mean the overview, there are multiple benefits of when using import-export. The first one, and we already spoke about this in previous presentation, is obviously to minimize any overhead on the target systems. So since you don't need, in a production OpenVX implementation, you will not need to revalidate the graph and to re-optimize the graph, the setup time is going to be much faster. Also, since you don't need to embed this optimization mechanics, the OpenVX runtime that is on the deployment system can be much smaller and much less complex as if you wanted to support the full graph creation, verification, and execution. And at the end, since you have much less code on the deployment system, it's much simpler to get certification. So we're speaking about ISO 26262 or MISRA, for instance. And another aspect and another advantage of the import-export is that since this graph optimization is supposed to happen offline, and offline you don't have timing or resource constraints, so you can really go deeper in terms of optimizations, and you can do offline what you could not do ahead of time. And typically, for instance, while I was speaking with people from FPGA, so if it takes 3 days to generate from an OpenVX graph a FPGA configuration, obviously you are not going to do it ahead of time. So you need to do it offline. So for DSP, you can generate some C code that is specialized for this graph and compile offline, and then you will get a sort of precompiled graph that you can just load on the deployment system. So this import-export extension opens really new possibilities, and in terms of possibility for the implementer, but also in terms of target systems. Okay, so now I will stop with the overview. So I will introduce the API. So first of all, when the application requests an object to be exported, we have several options. And the default option, so the one that you should use in most of the cases, is that you tell, okay, I want to export this object, but I don't care about the value of this object. So typically, I have an image, and I want to export this image. So the OpenVX implementation is going to export all what is needed to recreate this image, like the dimension, the format, some other properties. But you are not going to export the pixels, because you don't need, because the pixel will come from the camera on the deployment system. So this option, VX, IX, use no export value, is also the one that you need to use for the graph, because of course the graph, there is no notion of value really. So you need to use this option when you export a graph. But when you export a data object, you have the option to export also in addition the values. So you can use this VX, IX, use export values option for data objects. And there is a last option called the VX, IX, use application create. So typically here, it means that, okay, I want to export this object, but actually I don't want you to recreate it at import time. So I need this object, but I will provide this object, I will provide by myself this object to the import function. And this is what you need to use with images created from Handle, for instance. The export API is very simple. So you have two functions, and the most important is the first one, VX export objects to memory. So I put in blue the most important parameters. So this function takes a list of reference to the object you want to export. So this is the refs parameter. And associated to this list of reference, you need to provide the list of options, of export options that we were discussing before. So you need to have a correspondence, a one-one correspondence. If you export 5 objects, you need to provide 5 like options. So each object can be exported in a different way. And this export object to memory function is going to return this memory blob. So it is going to return a pointer. So you give the address of a pointer where you want the function to return the address of the memory blob. And it will return also the length. So this memory is allocated by the OpenVX implementation. So you can use it, but once you don't need it anymore, you need to inform the OpenVX implementation that you don't need this binary blob anymore. And for instance, if you already stored it on the file system, you don't need it anymore. And then you need to call VX release export in memory, giving the address that was returned by VX export object to memory. So to illustrate this, I show an example. And in this example, I have a graph that has some nodes, some virtual objects to connect the nodes, etc. And this graph has 2 inputs. For instance, one image called in, and a scalar, and it has one output that can be also an image. So in this graph, as an application developer, I don't want to export the scalar because this scalar for me should be a constant. So this is, I want to specialize my graph with this scalar as input. And I know that at import time, I don't want to change the value of this scalar. So in this case, you don't need to export the scalar. What you need to export is what you need at import time. So what you need to export is the graph, the input, and the output. And so this is what we do in the refs. So on the right, the refs array contains the 3 objects that you want to export. And in this case, we don't want to export the values. So we will use the VX, IX, use no export values for the 3 objects. And then at export time, this graph is going to be verified first, optimized, and all what is needed to be able to reconstruct something that has the same behavior at import time is going to be exported too. So this scalar object that I didn't specify in the reference list is going to be, well, at least its value is going to be exported, and automatically, because it's an input of the graph. So we need the value of the scalar to be able to build something at import time that will have the same behavior. The import API is also very simple. So we have 3 functions, but actually you don't need to use all the 3. So the main function of the import API is the first one, the VX import objects from memory. So this function takes, well, this function is going to return the objects that are recreated at import time. So what the application needs to do is to provide like an array of reference that is initialized to null, because it's an output in most of the cases. So you need to provide at import time an array that has as many objects that what you exported. So it needs to be the same number. And also, as a sanity check, at import time, you need also to provide the individual export, like object export options. You need to provide the exact same, so that in such a way, the import function can verify that what you want to import is consistent with what is in the binary blob that you are trying to import. So this function is going to return in the refs array the objects that are imported and that you can use after. So you are going to get graphs, images, and you can use them directly. You may have, so this function returns a VX import object, and the purpose of this object is also to be able to get well, access to the imported object from the name. Because we didn't speak about this, but in OpenVX, before export, you have the possibility to set a name to the object. So in such a way that at import time, you don't need to remember exactly the ordering of your objects. And you can just query this import object and tell, okay, please give me the object with this name. But in the hands-on, we will not use this feature. Once you are done with this import object, you can just release it. So when you release the import, the VX underscore import object, it doesn't mean that you are going to release the images and the graph. If you, because the application still has a reference to these objects. So this is this reference count management that is part of the OpenVX, and that Rada was like speaking about at the beginning. So if I keep the previous example that I took in the export slide, so what I will do if I want to export what I exported in the previous slide, I will provide like an array of reference with the 3 elements, and the 3 elements need to be initialized to null, and I need to provide a 3-element uses array also that contains exactly the same values as what we had before. I need also to provide like the address of the binary blob and the length. So this is what we got at export time, and then we import. And what is going to happen is that in this array, refs array that I gave to the VX import object from memory function, I'm going to get like 3 references. One a reference to the input image, a reference to the output image, and a reference to a graph. And this graph now is a sort of black box because you don't know what is inside. You cannot access what is inside. And this graph is also frozen, so it is specialized for the dimension of the input image and of the output image. You cannot just change the parameter of the graph with an image with a different dimension, because it will fail. So the graph is really frozen, what gives lots of opportunity of optimization actually. You can really specialize your graph at export time, what you cannot really do with, well, You can do it with the classic OpenVX way, but you have lots of bookkeeping in your implementation if you want to do this, because you need to detect when some dimensions of some parameters change, and then automatically you need to re-verify, re-optimize, etc. So in this case, with the import-export API, since the graph is frozen, you can really specialize your code at export time. So this is it for the the presentation of the import-export API. Now I'm going to present a little bit the hands-on and the use case that we are going to use. So, like I was saying at the beginning, we are going to use a key point detection and tracking use case as an example. So what the code that I gave you does is that every end frame, so for example 15, I think I initialize it to 15. So every 15 frames, we are going to detect key points in the frame using Harris corner. And then in between, we are going to track the key points. So why we detect every end frame? It's just because there are new objects entering the scene. So if we just track key points, we are not going to detect the new people, for example, who enter the scene. So we need to redetect from time to time just to make sure that what we track is consistent with the image that we have. So in the image on the right hand, you have for instance, the result of the detection. So it detects the interesting corners of the image, and it displays it as a red bullet. And on the left-hand side, this is what we get with the tracking. So we use the Lucas-Kennedy optical flow method. And so the red bullet is is the key point, is the position of the key point in the previous frame, and the top, the end of the arrow is where the key point has been tracked in the current frame. Okay, so I show you a little bit the different graphs that we have in the code. So the first one that I speak about is a tracking graph. So we have we take as input. So in this example, we use OpenCV to grab the data from the camera or from a file. So for this exercise, we have a file in the virtual image, and we use OpenCV to decode a MPEG video stream. And then we create an image from handle. And so Rada wanted that I speak a little bit about this. So it's not the purpose of this talk, but since we have some time, I can speak about this. So an image created from handle is a very important concept, because most of the time, the camera API has its own control of the memory. So it has a set of buffers. And in this case, you don't want OpenVX to allocate another buffer just to be able to create an image, an OpenVX image. So an image created from handle is very interesting because you are going to create an image object, but where you tell that the memory is not controlled by OpenVX. So this is not the OpenVX implementation that is going to allocate this memory and to control it. But this memory that contains the pixels is going to be provided by the application itself. So this image created from handle is like maybe just a structure that contains some information about the image, and so it's very small. And we have a functionality in OpenVX that allows the application to swap the handle. So, for instance, when you get a new input image from OpenCV, in this case, you just get the pointer to this buffer that belongs to the OpenCV world, and you tell OpenVX, okay, please now use this pixel buffer, and you swap, and the image is just going to point to this buffer. So this is what we use here. It saves memory, and it saves a copy also at the interface between OpenVX and the camera API. So we have this image created from handle, and we have a tracking graph that has 4 nodes. The 2 first nodes are used to convert a RGB image, color image, into a grayscale image. Then once we have the grayscale image, we compute a Gaussian pyramid that we put in the delay object. So we spoke also, like Rada spoke about the delay object before, and Tomer also. So because the Lucas-Kennedy optical flow method requires you to provide the Gaussian pyramid for the current frame and the previous frame. So because you track something from the previous frame to the current frame. So in OpenVX, we have this delay object that is a sort of array of objects that have the same properties. So if you have a delay of images, the different, you can decide how many slots you have in the delay. So in this case, we have 2 slots. So the delay contains, well, it's a delay of pyramids. So the delay contains 2 pyramids that will have the same property, the same dimension, the same scale, the same number of levels in the pyramids. And the difference between a delay and an array is that the delay can be edged. So we have a function in OpenVX that is called VX edge delay, and that automatically, what was in pyramid 0 in the slot 0 moves to slot -1, and what was in slot -1 goes back to slot 0. So it's like a rolling buffer. And the graph gets automatically updated. And actually, in terms of implementation, it can be done very efficiently just by swapping pointers. You don't need to copy data. So we have a delay of pyramid that needs to be given at the input of the optical flow node. We have also a bunch of parameters for the optical flow that I will not detail. And the optical flow takes also the key point coordinate in the previous frame, and is going to generate the key point coordinate in the current frame. And what is the current frame today? Well, now is going to become the previous frame when the new image comes from the camera. So this is why we also use a delay. So we have a delay of array of key points that is at the same time the output of the optical flow node and the input of this optical flow node. So this is the tracking graph. And we need also a detection graph. So with the detection graph is going to take the same image as input. It is going to do the same like RGB to grayscale conversion by using color convert and channel extract. And then, while it's relatively simple, we use the Harris corner node plus some like that is configured also with a set of parameters. And this Harris corner node generates an array of key points. And so when we when we execute the detection graph, it is going to generate the key points for the current frame. And then we edge the delay. So this information moves to the slot -1 of the delay. And then we can execute the tracking graph. Since the tracking graph also needs the Gaussian pyramid as input, so we added also the generation of the Gaussian pyramid in the detection graph. Even if it's not needed for the detection part, it's needed for the tracking part that happens just after detection. So that's pretty it for the delay. So now let's move to the practical part. So this is what you have in the virtual image. So if you have your virtual box open, and if you have booted the virtual image that we gave you, this is the same as the one that Tomer was using. So in this visual image, we have both the neural network demo and this import-export hands-on. So
working with him? Yeah, I think you can parallelly try what Tari is suggesting here. If you have the virtual machine up, you can try that.
Yeah. I suggest that you open the virtual box, and here it's a slide, but I'm going to switch to the to virtual box also in a few minutes. So you can just take a look like in real. And typically in this slide, this is what you will get in the import-export directory, in the home directory of the OpenVX user. So you have a set of subdirectories. The first one called data contains the video, the input video that we're going to use for the example. Then the two next directories called exercise 1 export, exercise 2 import are the starting point for you. So this is where this is the directory or this is where I've put the code that I'd like you to modify. So I will do it online also, so you can just do it on your own or just follow what I do. But this is what is in green and red is what needs to be modified by you. But since, by experience, we know that sometimes we don't have time, we have problems, so we provide the solution of the exercises. So if never, for instance, you are too late, you are too late to complete the export part when we start the import, you can still run the solution to the export exercise in order to get this binary blob stored on a file, and because you need it for the import side. So we have the solution to the exercises in these two directory. We have also like a util directory that contains some utility functions, so it's not really in the core hands-on code. This is, for instance, the interop code with OpenCV for the display, for instance, or some timer functionalities. We have also an OpenVX directory that contains a pre-built version of the Khronos sample implementation. So like Tomer was telling, the Khronos sample implementation is just functional, so you are not going to get wonderful performance with this, but it's at least it's good for this kind of tutorials, because we want to make you understand the API. So to show you the performance, it's more up to the vendors to do it, and this is what people are going to do in the afternoon with the vendor, like with the implementer's presentation. In this tutorial, we just provide what can be like shared public, like easily publicly. So this is the sample implementation. And then you'll see a build directory. So what I did is that I pre-built things so that it's simpler, we can go faster. So I don't ask you to run CMake and giving the good options. I just did it for you. And then you just need to do make in the build. So we also installed, because since I like you to touch a little bit the code, so it's not like deep programming, it's relatively simple, but I think it's always good to touch the code. It makes things more real. So since you will need to touch the code, we installed QTCreator in this virtual machine. And it's a simple IDE, but that is powerful enough, so it's convenient for this tutorial. This is what usually we use for tutorials. So, and what I'm going to do is that I'm going to switch to the virtual machine, just to show you how to start QTCreator. So let's start here. Okay. So I don't know how if it will be nice, because we have some delays and the internet connection, I think it's not so good. So, but anyway, okay.
Yeah, you haven't typed your password yet.
Yeah. Okay. Yeah.
That's
It's normal because I just do it now. Okay. So this is what you get when you enter. Oops. Okay. So when you log, you get something like this. It's totally empty. So what you can do to get a terminal is Control-Alt-T. And this is what I do with Ubuntu. Control-Alt-T is a shortcut to get Ubuntu terminal. I'm going to make things bigger a bit. Okay, so in the home directory we have some CNN stuff, and we have this import-export directory. Before going into the import-export directory, what I'm going to do, because there are some issues between QTCreator and VirtualBox actually. So I had to do a trick. So you need to execute QTCreator from the home directory for the moment. So this is what I'm going to do. So when you launch QTCreator, it's basically empty. So what I did to simplify things is that I configured QTCreator for this import-export project. So what you need to do is to go to File, the File tab, and then you go to Recent Projects, and you will see something related to import-export. So this is what you need to do. So we are just going to open up an existing project. And then you get all your source code in the left pane. So you see all what is compiled. So we have the exercise 1, exercise 2, solution, and we have the utility functions. So since Rada wanted me to speak about like image trees created from Handle, the first thing we can do is just to take a look at the code.
Terry, I have one question. Does anybody need help to be able to run QTCreator?
Yeah, so I will wait a little bit. Rada, please give me the green light when everybody is ready.
My file was damaged.
So Terry, you can continue. I'm just going to help off my screen.
Okay. So here I present the main function. So each exercise is structured this way. So we use C++ because it was more convenient for structuring the code. Because everything related to the tracker is put in a class. So we have, for instance, we have a feature tracker class that is relatively simple. Well, I will not detail it, but what we have inside this class is, we have a constructor that takes an image created from Handle as parameter, takes some Harris corner parameters, and an OpenVX context. And from this, it is going to create the graphs. And the graphs and the data objects are created with some internal functions that are not public here. And it keeps a reference to the two graphs here. So we have a detection graph. Maybe I can make it bigger. So is the size okay on the screen?
Yeah, Terry, can you increase the size a little bit?
Still increase, okay.
Hard to see from the last row. If you can just increase it just a little bit. 200%.
Still?
Frank, can you see it? No, it's a little high. Make it a little bigger. 200.
Well, it's...
Yeah, okay, that's good. If you can manage with that,
it's okay like this? Okay.
Yeah.
Yeah, because it cannot be too big, because otherwise we don't see anything anymore. Yeah. So this C++ class contains is going to create two graphs, the detection graph and the tracking graph. And both graphs, like I was showing you before, are going to use, they share some data objects like the delays and the input image. And the input image is here. It's kept here. It's input image from Handle. And we have the two delays here. So this is what actually we need to keep. And this is what we are going to export actually. We keep also the information about the graph, about the input image, so the format and the width and height. We keep a reference to the context. And that's pretty it. So it's what we need. It's all we need actually. And as public function, we have detect key points. So we just need to since we use an image created from handle, we don't need to. This function does not take an image, an OpenVX image as input, but it takes a pointer to the buffer that contains the pixels. So we just need to provide the handle. And we have a function to track the key points, and it takes also the handle. And this is pretty it. And what we are going to do, we are going to work in this function, export to file function. So I will come back to this later. And what I wanted to show before is how we create an image from handle. So this is the main function. The main function, the first thing it does is to create a context. Then, since in case of, well, it's not mandatory, but in case of error, you want to get the notification of the error in a textual form. You don't want just a status. You want to understand what happens. And this is typically what you want for when you verify a graph, because when the graph verification can be a complex, it's going to do plenty of things. And you can have very different, lots of different types of errors, and the error status that is returned is poor in terms of information it conveys. So this is why actually we prefer to get some textual information. So what we do here, we register a log callback, and a log callback is a function that I provide, and this log callback will be called in case of error, or in case the OpenVX implementation wants to give me an information. So this log callback we can see. It's so the prototype of the log callback is a standard. So it should take a context first. A reference should be the second parameter. So the reference is the object involved in the message that is given to the callback. Then we have a status. So it tells me which object is involved in which error. And then we have a string. So what my callback does is just, okay, it's just going to display to the screen the string that was given. So this is very simple. Okay. So I go back to my code. Then what I do is that I'm going to get a first frame from OpenCV. So here, this is some OpenCV code. So depending on the command line, I may open the webcam, or if a file name is given in the command line, I'm going to open a video file in the file system. So this is what we will use in this exercise. Then, okay, so I open my video stream. Then I call OpenCV. I tell OpenCV, please give me an image. So what OpenCV does is that it doesn't return a RGB format. Actually, it returns a BGR format. So the first thing I need to do is to use still OpenCV to convert between BGR and RGB. So we are going to have a copy here. It's not very nice, but while this is we use OpenCV just for a demo. In a real product, we will not use OpenCV, I think. So we use this CVT color function to get a RGB image, but still OpenCV image. And this is where we are going to translate the OpenCV world into the OpenVX world. So the OpenCV allocated some memory to store the pixels. So what we do is that we ask OpenCV, give me a pointer, give me the address of this buffer. And this is what we do here, cv src.rgb.data. So this is OpenCV code. And we get this src pointer, this address into this src pointer local variable. And then we do what is needed to create an image from handle. So when we create an image from handle, we get typically OpenVX needs to adapt to the memory layout of the user of the application. So in this case, we are going to ask OpenVX to adapt to the memory layout given by OpenCV. And the OpenCV images are like you can have a pitch, you can have a gap between lines. You don't have gaps between pixels, but you can have a gap between lines because OpenCV may prefer to align the beginning of each line on a certain boundary. If never you want to do some vectorization when you execute an OpenCV function. So, and OpenVX supports this kind of layout. And actually, OpenVX supports more because OpenVX supports also gaps between pixels. Well, most of the implementation will not like it too much, but you have the possibility to express a gap between pixels in the OpenCV or in the OpenVX memory layouts. So what we need to do in OpenVX is to create a VX image patch addressing structure. And this structure will contain the size of the image, and it will contain the stride X and stride Y. Stride X gives you the number of bytes between the beginning of two successive pixels in a line, and stride Y gives you the number of bytes between the beginning of two successive lines in the image. So the stride Y for OpenVX is similar to the step in OpenCV. And since the pixels, the RGB pixels are like put one after the other in the OpenCV images, the stride Y is simply 3, like it's the size of a RGB pixel. So each R, G, and B are 8 bytes, are U8. So it will be 3 times the size of U8. So once we have created this structure, we can create an image from handle with this function. VX create image from handle. We give a context because any object in OpenVX is created inside a context. We tell which format it corresponds to. So in this case, it's RGB. We give the address of this addressing structure that defines the memory layout. We give the address of an array of pointers that contains the address of each of the planes of the image. So RGB image contains only one plane, so we just need to provide one address. So this is why I provide the address of this pointer that I initialized earlier. And then we have an option. We have a placeholder so that vendors can extend images created from handle. So here we say that by telling it's the VX memory type host, we tell that the memory that we provide is a host memory. So this is the same memory environment that the one that in which the application is executed. But if you have a GPU, if you have a DSP with different memories in your system on chip, you may want, as a implementer, you may want to extend this. And for instance, we could tell, okay, well, what I give you is not a pointer to the host memory, but this is a pointer to a CUDA buffer, for instance, or this is a CL buffer. And this is not required in the core spec, but any implementer can extend this. And in such a way, if you get your input image already in the GPU memory, for instance, and you want to do the processing on the GPU, you don't need to go through you don't need to copy this data into the host memory and then to copy it back to the GPU memory. You can do directly. The memory is already there. You inform OpenVX that it's already there, and OpenVX is not going to have to move anything. So it's pretty actually interesting as a feature. So in this exercise, of course, we use the Khronos sample implementation, so it just supports the host memory. So this is what we do here. And then, we have a macro just to check that the image was correctly created. So Radar, I think Radar was speaking about this. So the way we check that everything was fine with an object creation in OpenVX is to call VX get status. And this function is generic, so it works with images, with pyramids, with graphs, with anything. So it takes a VX reference parameter. So we need to cast this. In this case, it's an image that I created. So I need to cast this VX image reference into a VX reference. So like Rada was explaining. Okay, I come back here. Then
So
I create my C++ object.
So Thierry, I just want to
Yes?
give you a time check. It is 12:15 now. We have 14 more minutes actually for the lunch.
Ah, okay, because I thought I had time, but actually I don't. Okay, I don't have any more. Yeah, okay. So okay, so that's it about this rapid presentation. So I will go back to my slide. Yeah, so we are running out of time now. So in this slide, this is how we build the exercises, and what I'd like you to do is just to test that it works, because it's already pre-built. So I'm going to do it online. Okay, I go back to my virtual machine. So what I'm going to do is that, oops, I'm going to create a new terminal, and I go to this import-export directory. I go to the build. So this is already built. Everything is built already. So if I do make, nothing should happen. And the way I am going to check that everything is fine is I'm going to call, for instance, the first exercise. So I go to bin, exercise 1, export, and I give as a parameter the file that we have in the data folder. So it's called pets09 something. So here, when you execute this, you should have like the feature tracker, detector and tracker that works. And why it does this? Because before exporting, when I create the graph, I verify it. I want you to export it, but actually just to check that it works, I execute the graph directly, independently from the fact that you export or not. So you should have something that moves on the screen. If you have this, it means that you are good to continue. Okay, then I will go back to QTCreator. And what we need to do is we need to go to the feature tracker.cpp file, and we need to do what has to be done in the export to file function. So here the goal was for me not to make things too difficult. So each step is explained what we need to do. So I think we have 4 steps. And in many cases, you just need to uncomment and just fill the holes. So I'm going to do it live because we're running out of time. So maybe you can do it after the tutorial also at home. So let's start. So so here everything is already created. So my graph is created, my data objects are created, and what I want to do is to export. So I will come back to my slide. Yeah. So what I want to export is 5 things. It's what I need to execute the algorithm at import time. So I need to export the input image. I need to export the 2 delays, and I need to export the 2 graphs, and that's it. So how I'm going to export them? So most of the objects are going to be exported with VX, use no export value, so this is the default export way, except the input image, because since it is created from handle, the import function is not able to create it, because it doesn't have the handle at import time. So we need to export this image created from handle with this option, where we tell that actually we don't ask OpenVX to recreate this object. the application is going to provide this object to the import function. So this is what we want to do actually. Then we go back to the code and we start to do the export. So the first thing we need to do is to create a list of objects that we want to export. So this is what we have here. This is the step 1. So what I'm doing is that I'm uncommenting the declaration of the reference list. I have already the image created from handle there. I have the detection graph. I just need to fill the holes. So I need also to export the tracking graph. So the tracking graph, well, we can deduce the name from the detection graph. Oops. I have an issue. Okay. So QTCreator is quite good because it helps you with the auto-completion, but here it's not enough. Okay. I need to convert my tracking graph into a VX reference. And since the detection graph is called detection graph underscore, I assume the tracking graph will be called the same way. Good, it's red, so it means that it's okay. Then I want to export the delay of pyramid. So I have exported the delay of key points after. So I'm going to do the same. First, I need to convert into a VX reference. And obviously, my pyramid delay will be called pyramid something. Oh, good. Pyramid delay. So you just need to put to start the name and auto-completion will propose something. And here it proposes pyramid delays underscore. So I'm good. I think I'm good. I have my image, my 2 graphs, and my 2 delays. We can move to the step 2. And step 2 is to create the option, the export option list that must have, where we must have 1 item per object that we want to export. So, oops, I did a mistake. So I'm going to uncomment. And what I need to do is I need to choose in these options. So this is what I was telling in my previous slide. So most of my objects need to use the no export value. So the key points. Oops. So detection graph, tracking graph, the delays are going to use this. And the specific case is the image created from handle that needs to be exported with this option, application create. And I think I'm good here. Okay. Then I create local variables just to make sure that the export function can return the address of the binary blob and the number of bytes in somewhere. And then the step 3 is to call this export object to memory function. Okay, I will just move it to have more space. So this function, well, I can go to this function. So with QTCreator, I can go directly to the header. So the header is called VX khrix.h file. So khr means it's an official Khronos extension. So what I need to give is a context, a number of the number of objects that I want to export, and the array of objects, the array of options, and then the address of the pointer where I want to get the address of the binary blob, and the address of the place where I want the length to be returned. So what I need to give here is a number of objects. So I have five objects to export, so 5. I need to give the list of references, what I did before, and I need to give the list of options. And I think I'm good here also. So QTCreator doesn't complain anymore, so it seems to be good. And Finally, so this function is supposed to return the address of the memory blob in blob ptr and the length in blob byte. So I'm going to print this to the screen. And then I generate the file. I release, and what I need to do at the end is just to release the exported memory. So this is what I need to do in step 4. So in step 4, I just need to uncomment. I tell, okay, now I stored what you gave me on the file, and I don't need this memory anymore, so you can just recycle it. And so this is it. So hopefully, after this function is called, I will have a file called, I don't remember. So called something. So we will check in the directory, and that has a size that is different from 0. So this is what I'm going to do. I'm going, first of all, so I saved with Control S in QTCreator, and I'm going to build. So I don't have any compilation error. And then, in my current directory, I have this file, exported tracker.bin, that has a size 0, because previously, to check if everything was okay, I just executed the exercise 1 that was not complete. So what I'm going to do the same. So I call this exercise 1 export executable on the input video. Okay, I stop it. And then it seems that it worked, because it tells me that I got an export blob at this address, and with a number of bytes that is different from 0. So it seems that we have something. And we generated this file, exported tracker.bin. So I'm going to check. So, and indeed, we have this file that has this size. So it seems that we are good here with the export. We exported something. We don't know if it works, but we exported something. And the next step is to check, well, if we can import it. So I will go fast, because we are really running out of time. So
Sorry,
the step is in...
can you walk through the solution too for the import?
Yeah. I can work through the solution rapidly. Okay, so I go to the solution to import. And then the only difference is that we need to provide the image created from handle. And then we import.
Okay.
So it's very simple. So you can just work yourself, maybe.
Yeah. So I think now it's lunchtime and we have the problem with audio. Maybe you guys can just go this offline. If you have any questions, you have Khronos forums where Thyri is going to be looking at it, and a lot of our working group members will be looking at it, so we can kind of continue further discussion there. Will that be okay? Okay, great. Okay, thanks, Hari. I put you on speakerphone if you want to say closing remarks. I'm connecting speakerphone to the microphone, so you can still reach out to the audience.
Yeah, the technology is not so reliable. Yeah. So well, the import side that you have on screen, I guess, is very simple. So you just need to create a reference that you initialize with null, and the import function will just initialize what you have as null here, and will give you an object. So basically, you will get everything you had at the time you exported. So you can look at this code. It's not very complex. You can look at the exercise 2 import code in this feature tracker import cpp.cpp. It's everything is at the very, very beginning. There are some explanations, some steps, and so it's relatively simple. The concept is not that complex, so you should be able to do it offline. Okay, so that's it on my side. So.
Okay. Thanks, Hari. So we are going to have a lunch break for an hour. So
okay.
We'll try to follow up later. Are you going? You okay?
Okay.
Okay. We'll exchange
okay.
emails on that.
So have a good.
Okay.
But Bon
Thanks.
appetit. Have a good lunch.
Yep. Thanks a lot, Terry.
Thanks.
Bye.
Bye-bye.